The big question for this segment is, what is the observational evidence for the Big Bang? Well, by means of an introduction, I will tell you straight away that we're now living in an incredible era of precision cosmology, where we actually know the age of the universe to a few tens of millions of years, and that age is 13.8 billion years. How do we know this? Well, it's thanks to all the major recent advances we've made in modern telescopes and the ground and space-based instrumentation. But not so long ago, our understanding was actually quite different. As a boy, there were two competing theories for the origin of the universe. One was a so-called steady-state theory postulated by Sir Fred Hoyle, and in this theory the idea is that matter just spontaneously comes into existence, and that as the universe expands more matter is created, so that when you look at any direction in the universe it looks essentially exactly the same on the larger scales, and this is known as the cosmological principle. But the alternative theory was something which he jokingly called the Big Bang, where the universe suddenly started from an infinitesimal point and expanded thereafter. He used this term in a derogatory sense in competition with his steady-state theory, but it's now the steady-state theory that is obsolete and the Big Bang theory that has taken centre stage. And how did we get there? It's because of observational evidence. And this started fundamentally in 1929 when Edwin Hubble, a famous American astronomer, discovered that the distances to faraway objects called galaxies, that these distances were very strongly correlated with their redshifts. You may have heard of that term, but basically what it is, it's a bit like, you know, you're standing there in a railway station and a big express train is coming through very fast without stopping, and you hear the sound go. That's with sound waves. As sound waves, as the train approaches, those sound waves get compressed. As the train goes away from us, those sound waves get stretched out, and that has the effect of making the pitch change. It's similar with light, which is also a wave. So as objects like galaxies start to recede away from us, the wavelengths of light get stretched out. And as the wavelengths get longer, that makes them redder, hence redshift. So all the objects in the universe which are receding from us with the speed that is linearly proportional to the distance is the redshift. So Hubble's observations showed that distant galaxies, regardless of position on the sky, have an apparent velocity, which is as measured from their spectral lines, which increases with distance, i.e. the further away a galaxy is, the greater the apparent velocity of recession. Now, if we assume that we're not by some incredible chance of nature at the very heart and centre of a gigantic explosion, from which all matter is receding then in every direction, then the only remaining interpretation, i.e. we're not in some special place, the only remaining interpretation is that all observable parts of the universe are moving away from each other, and that if we trace all of this movement back in time, we get back to a common point of origin. This common point of origin is known as the Big Bang, and it is at that point when our universe came into being. So we have some direct observational confirmation of the Big Bang. This first came in 1964 with the discovery of the famous cosmic microwave background radiation by Penzias and Wilson. They worked for the Bell Labs in America, and they're using a sort of a microwave feed horn sort of antenna thing that looks like a big ear, and they had this strange noise. They couldn't understand what it was when they were doing their work. First of all, they thought it was maybe pigeons nesting inside this little ear antenna thing, but it turned out that it was actually the relic of the Big Bang. This noise was in fact the cosmic microwave background radiation. Later, thanks to spaceborne experiments, for example, the Cosmic Microwave Background Explorer, COBE, and the Wilkinson Microwave Anisotropy Probe, WMAP, these have measured the tiny temperature fluctuations point by point across the whole sky. And when they do this, they create what's known as the Cosmic Microwave Background Spectrum. And now we have all sky temperature differential maps for the oldest light in the universe, which is what the cosmic microwave background radiation is. This was emitted when the universe was only 380,000 years old. Now this occurred at the so-called epoch of recombination. I'll tell you a little bit about that later. But what it does when you look at the cosmic microwave background radiation in detail, you might have this beautiful 3 Kelvin black body radiation map, but if you actually look in detail and look at the very tiny fluctuations away from that, you see that there's slightly different temperatures on one side and the other, and you create a map of temperature fluctuations. These tiny little temperature fluctuations correspond to slightly different densities in the early universe, and they represent the seeds of all future structures that we see today. All the stars and galaxies and clusters of galaxies and large-scale structures and filaments and voids have been seeded in the early universe by these small differential temperature fluctuations. So what is this so-called epoch of recombination I've mentioned? Well, as you can imagine, immediately after the Big Bang, the universe was extremely hot and dense. Normal atoms, as we see here today in me and around us, didn't exist then. All matter was actually existing just as a highly ionized plasma. The universe expanded, and as so, its temperature and density fell until, as I said, about 380,000 years after the Big Bang, the physical conditions then allowed ions and electrons to combine for the first time to produce stable neutral atoms, like hydrogen and helium. When this recombination occurred of ions and electrons to form a neutral atom, that is known as a so-called epoch of recombination. So, 380,000 years after the Big Bang, universe cooled so that the previous plasma of ionized gas becomes neutral, epoch of recombination. At this point, the universe's matter also became transparent to radiation. Note, completely ionized matter can absorb any wavelength radiation, while neutral matter can only absorb specific quantized wavelengths that carry the exact energy that match energy differences in the electron shells around the atom. The temperature at which this transition occurred from ionized to neutral, called the moment of decoupling, occurred at a temperature of about 3,000 degrees Kelvin. The radiation had a black body spectral shape, as predicted, but the peak in the currently observed microwave background has a temperature of only 3 degrees Kelvin, actually 2.726. But as you can see, there's a factor of over 1,000 between the original temperature at the moment of decoupling in the early universe, 380,000 years after it first came into existence, and what we see now. And this is because the entire spectrum has been redshifted from the time of decoupling, when the temperature was 3,000 degrees Kelvin, by the subsequent expansion of the universe until we measure it today as 3 degrees Kelvin. So basically, as the universe expands, the CMB wavelengths of radiation expand by the same factor. So following Wien's blackbody law, which says that the wavelength peak of the cosmic microwave background spectrum is inversely proportional to the temperature of the cosmic microwave background, so the drop in the CMB temperature by a factor of 1100, that is from 3000 K down to 2.726 K, this indicates an expansion of the universe by a factor of 1100 from the moment of decoupling until now. Now, this is not a little talk about medieval history, but I'm going to talk about the dark ages of cosmology. This is a so-called cosmological epoch which represents the period of time between the release of the cosmic microwave background radiation, about 380,000 years after the Big Bang, and the formation of the first stars, a few hundred million years after the Big Bang. Now, in between, the universe was effectively dark because although radiation could pass, there were no sources of objects to emit any light. The first stars hadn't yet formed. But understanding this dark age period is crucial for our understanding of cosmology, since it indicates when the first structures formed in the universe through gravitational instability. In particular, when the very first stars formed, a few hundred million years after the beginning, when the first galaxies then formed from those and collapsed together to form supermassive black holes in the centers of some of them, and all the large-scale structures that we see today. So I said at the very beginning, we are in a period of precision cosmology, where what we know about the universe today has been completely transformed by what we knew 20 or 30 years ago through all these incredible new experiments and telescopes and satellites that we put into space to measure things like the cosmic microwave background. We now know with precision what the Hubble constant is. We know how old the universe is. And yet there's still a lot of things we don't understand. We don't understand why the Big Bang happened. We don't understand what happened at the very instant of the Big Bang yet. We can't get right back to that original T of zero time yet.